Today, we want to continue looking at vector spaces and subspaces. This is where we kind of roll over from the end of chapter 2 and kind of like start dialing in a little bit more chapter 4, looking at vector spaces of things that are not just in Rn, but then making all those vector spaces look just like Rn. That's our goal. So let's talk about some important subspaces of Rn. In particular, we want to talk about the column space and the null space of a matrix. The column space of a matrix is just the span of the columns of the matrix. So the column space of a matrix is the span of the columns of the matrix. The null space of a matrix is the solution set to the homogeneous equation. So the column space of a matrix A is the span of the columns of the matrix. The null space of a matrix A is the solution set to AX equals 0, the homogeneous equation. What we need to know before we start talking about this is how we describe a vector space. To describe a vector space or a subspace, we want to build a basis that's a linearly independent spanning set. So first, we go for a spanning set of vectors, and then we cut it down to a linearly independent spanning set. So our notation for the column space of A is column space of A. I will often put it in parentheses when I'm writing so that we don't just read this as cola. And the null space is denoted null space of A. We're so obsessed with 3-letter abbreviations that we're just going to abbreviate null space with NUL, even though the other letter is only wafer thin and it just be another L there, but nope. Sometimes I put the wafer thin L right in there, so who knows. All right. So let's take a look at this matrix A, 1, -3, -2, 6, and 5, -15. What we want to do is find where the pivots are. Oh, wait, I got to talk about the size and where these spaces live. So if A is M by N, then the column space of A is a subspace of Rm. This makes sense. We're making a linear combination of all the columns of A. The columns of A are in Rm, if A is M by N. And so any combination of those columns will be in Rm as well. The null space of A is in Rn. So the null space is the set of solutions to AX equals 0. So the null space is these x's in here. And if A is M by N, then the x's have to be from Rn for this multiplication to be defined. So if A is M by N, then the null space of A is a subspace of Rn. We want to be able to describe the column space and the null space in more than just general terms. We don't, if I give you a specific matrix A and I say, what I'll do is I'll say, find a basis for the column space of A. You don't just want to say that the column space of A is the span of the columns of A. That's just giving me the definition of the column space of A. I want for this particular matrix, what is a basis for the column space of A. So to find a basis for the column space of A, just grab the pivot columns. The pivot columns of A are a basis for the column space of A. The way we're going to find the pivot columns is write the reduced row echelon form, but that's just going to tell us where the pivots are. I see a lot of us are still making the mistake of saying the reduced row echelon form has a pivot in every column. And to which I responded, well, what about the original matrix? Does the original matrix have a pivot in every column? And the answer is yes. The reduced row echelon form is just what we use to find where the pivots are. The pivots are in the matrix itself. The matrix has a pivot in every column or doesn't have a pivot in every column. You don't want to specifically call out the reduced row echelon form because you're implying that the reduced row echelon form has pivots when the original matrix does not, and you don't want to express that thought. You don't want to bring that up as a possibility. So to find a basis for the column space of a matrix, all we have to do is find the pivot columns. So in this case, we have the matrix 1, -3, -2, 6, and 5, -15. I picked this matrix because it was really easy to reduce. The reduced row echelon form is going to be 1, -3. Oops, sorry. So I'm going to get 1, 0. And what you notice, if I do -3 times the first row, or if I do 3 times the first row and add the second row, I'm going to cancel out the second row entirely. This makes sense because if we look at the columns of A, the second column is just -2 times the first column. And the third column is just 5 times the first column. And that's what the reduced row echelon form is telling us. So we have just this pivot in the 1, 0. And this pivot in the first row, first column. And so when we go to the original matrix A, there's a pivot there in the first row, first column. The reduced row echelon form shows us where the pivot is, but the matrix has a pivot in the first row. The matrix A has a pivot in the first row, first column. So a basis for the column space of A is just that vector 1, -3. Look at everything that I've written here. A basis for the column space of A is this vector 1, 3. That is every linear combination of the vector 1, every scalar multiple, because there's only one of them. Every scalar multiple of the vector 1, -3 is in the column space of A. Notice that I did not write the column space of A is equal to 1, -3. If you wrote this, because you didn't want to write all this, that's so much writing. If you just write the column space of A as 1, -3, you're telling me that there's only one vector in the column space of A, and that's not the case. There are infinitely many vectors in any non-zero subspace. So a basis for the column space of A is 1, -3. We're just grabbing the pivot columns from the original matrix A. I don't want to say a basis for the column space of A is 1, 0. If I just have the vector 1, 0, I can't get a -3 in the second as the second entry. You got to grab the vectors for your basis from the original matrix. To take this one step further, since there is one vector in a basis for the column space of A, that means the dimension of the column space of A is equal to 1. Dimension is the number of vectors in a basis. The dimension of a vector space is the number of vectors in a basis for that space. The dimension of a vector space is the number of vectors in a basis for the space. So in this case, we see that the dimension of the column space of A is equal to 1. The dimension of the column space of A is also known as the rank of A. So those of you who have been using rank arguments but not knowing what the rank is, there's what the rank is. The rank of a matrix is the number of pivots in the matrix. So the dimension of the column space of a matrix is the rank of the matrix. So the rank of a matrix is the dimension of the column space of that matrix. So let's switch over to the other side and talk about the null space of a matrix. To find the null space, basis for the null space of the matrix, we just need to write the solution set to the homogeneous equation AX equals 0. So if we take a look at this matrix, we got 1, -3, -2, 6, 5, 15. We have the reduced echelon form of the matrix. If we imagine this, if we imagine the augmented matrix for AX equals 0, we'd have 1, -3, -2, 6, 5, -15, make an augmented matrix for the homogeneous equation. Normally, we would not do this because we know what's going to happen to the last column, and that's nothing. But we can use this to emphasize the fact that there are 3 x's. There's x1, x2, and x3, and then the zeros for the constant. We would not want to read the whole matrix A as an augmented matrix. We want to make an augmented matrix so we could write the solution set. So we have an x1, an x2, and x3. We can see that x1 is -2x2 minus 5x3. So our general solution looks like x1 is 2x2 minus 5x3. x2 is free, and x3 is free. So here we will first write the general solution to the homogeneous equation. Then we'll write the solution to the homogeneous equation in parametric vector form. So there are the three entries. I'm going to have an x2 vector. That's going to be 2, 1, 0. And then I'll have my x3 vector, which is going to be negative 5, 0, 1. So a basis for the null space of A would be these two vectors. Notice that A is 2 by 3. So the column space is a subspace of R2, and the null space is a subspace of R3. In this case, we'll notice that the dimension of the null space of A is equal to 2, because the dimension of a vector space is the number of vectors in a basis for the space. So the dimension of the null space of A is 2. Once again, notice I'm saying that this is a basis for the null space of A, and it's these two vectors. Because what I'll ask you to do is find a basis for the column space, find a basis for the null space. One thing that we want to note, one important result, thing that we want to note is that the column space is the span of the pivot columns of A. And for each non-pivot column, that gives us a free variable in the solution set to the homogeneous equation. So this gives us the rank theorem, which says if A is m by n, then the rank of A plus the dimension of the null space of A is equal to n. If A is m by n, then the rank of A plus the dimension of the null space of A is equal to n. This makes sense because n is the number of columns, and each column is either a pivot column or a non-pivot column. So n is the number of columns. Rank of A is the number of pivot columns. And the null space of A, the dimension of the null space of A is going to be the number of non-pivot columns. Because for each non-pivot column that in the matrix, that gives us a free variable in the homogeneous equation. And so the number of non-pivot columns will be the dimension of the null space of A. So the rank theorem just says that a column in a matrix is either a pivot column or a non-pivot column. Any questions? All right, let's pause the video here and grab us some more examples of finding a basis for a space. Oh wait, before we do that, notice that the column space is a one-dimensional subspace of R2. The column space of A is if A is a 2 by 3 matrix, then the column space of A will be a subspace of R2. In this case, we have a one-dimensional subspace of R2, and so that'll be a line through the origin in R2. When we look at the null space is a subspace of R3. And we have a two-dimensional subspace of R3. So that will be a plane in R3 through the origin. So we want to think about things geometrically whenever we can. Now let's pause the video and grab some more examples.